Hello and welcome to the Moxy tutorial series. This lesson is titled, What is SmO2? There are two sections in this presentation. The first will cover the definition of SmO2. This is going to be a technical discussion on precisely what SmO2 means, what is actually being measured, and where in the body the measurement is taken. The second section is going to introduce the concept of supply and demand for oxygen in the muscle. This is intended as a starting point for learning to interpret how various physiologic conditions contribute to the SmO2 reading. So let's get started with the definition of SmO2. SmO2 is the percentage of hemoglobin and myoglobin that is carrying oxygen in the capillaries and tissue of the muscle. This definition covers a lot of ground, so we'll break it down over the next several slides based on three elements of the definition. The first element is that SmO2 measures hemoglobin and myoglobin. These are oxygen-carrying and storing molecules within the body. The optical technology that Moxy uses measures the color of these molecules to determine SmO2. The second element is that SmO2 is a percentage of the molecules that is carrying oxygen. This can range from 0 to 100%. And the third element is that SmO2 is measured in the capillaries and tissue of the muscle. The capillaries and tissue of the muscle is where the oxygen is being consumed. So this leads directly to the supply and demand for oxygen concept. Also, Moxy is designed to be maximally sensitive to the muscle layer and minimally sensitive to the overlying skin and fat layers. Next, we'll look at these elements in a little more detail. Moxy measures hemoglobin and myoglobin. Hemoglobin is the molecule in the red blood cell that carries oxygen. It's responsible for the vast majority of oxygen that's transported from the lungs to the rest of the body. Hemoglobin picks up oxygen in the oxygen-rich lungs and releases it when it gets into capillaries where the surrounding tissue requires oxygen. Hemoglobin is what gives blood its deep red color and changes color from bright red when it's oxygen-rich to dark red when it's not. This change is what Moxy measures. Myoglobin, on the other hand, is a molecule that is stationary in the muscle tissue that stores oxygen. It's what makes red meat red. Mammals that can hold their breath for long periods of time, like whales and seals, have huge amounts of myoglobin in their muscles because of the oxygen storage capacity. The color of myoglobin and its change of color with oxygenation is the same for both myoglobin and hemoglobin, so the Moxy measures both molecules together. The next element of the definition is that SmO2 is a percentage of the molecules containing oxygen, as opposed to a measure of the total amount of oxygen present. In this first example, we show 4 hemoglobin or myoglobin molecules. 2 are oxygenated, representative of their red circles, and the other 2 are deoxygenated, which results in an SmO2 of 50%. In the second example, there are many more molecules of hemoglobin or myoglobin, but the SmO2 is still 50% because half of them are carrying oxygen. The difference between these first two examples would show up as a difference of the total hemoglobin value, or THB, which is discussed in another lesson. The third example shows that if all of the molecules are deoxygenated, the SmO2 would be 0. And by now, this final example is pretty self-explanatory. The next aspect of the definition of SmO2 is the location of the measurement. This simplified diagram of the circulatory system shows the heart, lungs, brain, and skeletal muscle. SmO2 is measured in the skeletal muscle, and more importantly, it's measured in the capillaries and tissues of the skeletal muscle. You can see on the diagram that the measurement is taken right where the blood changes from red to blue. This indicates that SmO2 is measured at the point where oxygen is being consumed. This directly leads to the concept of supply and demand for oxygen that's presented in the second half of this presentation. If more oxygen is being used than being delivered, the SmO2 will go down. Note that this is very different measurement location than where a pulse oximeter measures. Pulse oximeters are designed to sense the pulsation in the optical signal that is caused by arteries expanding and contracting with each heartbeat. This makes them sensitive only to arterial blood. Since no oxygen is consumed in the arteries, this reading is usually higher than 90%. However, SmO2 values are commonly anywhere in the range from 0 to 100%. Let's take a look at how Moxy works. This sketch shows how Moxy is able to isolate the SmO2 reading to the muscle layer. The Moxy works by shining light into the tissue at one point. The light scatters in all directions, and you can observe this by holding your hand over a flashlight. Your entire hand will glow with pink light because the light is being scattered throughout the tissue. The same thing happens with the Moxy light. Since the light is scattered in all directions, most of it is lost. However, a very small fraction of the light will make it back to the detector optodes and is delivered to the detectors in the sensor. The detectors are at different distances from the emitter, which allows the Moxy algorithm to isolate the signal from the muscle layer. You can see here in the picture the light emitters and detectors on the bottom side of the Moxy sensor. The emitter blinks a red light to take the measurements. Now that we have an understanding of what SmO2 is, we can start the second section of the tutorial that'll look at how to interpret the data. The first level of interpretation is to look at the concept of supply and demand for oxygen in the muscle. The supply of oxygen is controlled by blood flow to the muscle. There are a host of reasons that contribute to blood flow, and we will look at these in greater detail in future lessons. Some of these even cause the supply and demand analogy to break down a little bit, but for now we will consider blood flow to be oxygen supply to develop our basic understanding. Demand will be simply the utilization of oxygen within the muscle. More utilization equals higher demand. Again, there are many factors that contribute to demand, and these will be covered in later lessons. For now, demand is how much oxygen the muscle is using. At this point, we want to stop and offer some warnings. It may be very tempting for you to jump ahead and make the connection that SmO2 can tell you when a muscle becomes anaerobic. The first warning, which you've probably already heard, is that both the aerobic and anaerobic metabolisms are generally always occurring in the muscle. The body doesn't suddenly switch from one energy system to the other. Some people would actually prefer to use the term oxygen-dependent metabolism and oxygen-independent metabolism instead of aerobic and anaerobic to be clearer on this point. The second warning is that SmO2 by itself does not tell you directly how much energy is produced aerobically versus anaerobically. It is possible to have a very low SmO2 and still be producing energy mostly from aerobic pathways. It's also very possible to have a high SmO2 and be using significant amount of energy from the anaerobic pathway. Let's now look at the relationship between supply and demand for oxygen in the muscle in several hypothetical conditions. The first condition we want to consider is rest. The oxygen supply is low at rest. The heart rate is not elevated, and the blood vessels are not dilated, so the blood flow to the muscle is small. The oxygen demand is also low at rest. The muscle is using very little oxygen. This means that SmO2 value could be anywhere in a wide range. We typically see SmO2 values from 40 to 85% in rested muscle. The supply and demand are both small, so a small change in either one can make the SmO2 rise or fall. There may be some possible uses for monitoring resting SmO2 values or seeing how they trend over time, but at this point it's not a primary input for training athletes because we want to see what happens when they are actually performing their sport. The second condition to consider is the case of isometric exercise. In this case, the blood flow can be very small. This type of exercise typically doesn't induce a large increase in cardiac output. Also, the static muscle tension tends to reduce blood flow locally to the contracted muscle. On the demand side, the muscle is using a lot of energy to produce strong contractions, so oxygen utilization will be high as long as it's available. This combination of low supply and high demand can only lead to a low SmO2 value. In the demonstration portion of this lesson, you will perform an isometric contraction yourself and observe these results directly. The third hypothetical case is where the muscle's ability to consume oxygen is limited while performing the sport. Ultimately, one of the goals of using Moxy is to identify which physiologic system is limiting an athlete's performance. This identification process requires more complex analysis than just looking at SmO2 while performing at steady state. For now, we are just looking at how SmO2 responds when the muscle doesn't consume all of the oxygen that is delivered. If the athlete is running like in the photo, presumably the blood flow will be elevated so the supply is high. However, if they are not consuming all of the available oxygen, the demand is smaller than the supply. This will make their SmO2 to be medium or even high. The fourth case we want to consider is when the available blood flow is not sufficient to meet the needs of all the working muscles. A well-trained double-poling cross-country skier might be a great example of this. The cardiac output is very high. However, the athlete is using all of his large skeletal muscles at the same time. The central nervous system acts autonomously to maintain blood flow to the vital organs and brain, so it may restrict blood flow to the skeletal muscles if it has to. The demand situation is very high because the athlete is well trained. His muscles are very good at consuming oxygen. Of course, this then leads to a low SmO2 situation. The final case we want to consider is recovery. When the athlete completes a workout or a race, the blood flow continues to be elevated even after the workout is complete. The heart rate will be elevated and the blood vessels in the working muscles will remain dilated for some time. However, the demand for oxygen almost drops immediately once the exercise has stopped. This leads to the situation of a high SmO2. Very often, the SmO2 will be higher in this case than it was at rest before the exercise even started. In this tutorial, we've covered two primary concepts. The first is the definition of SmO2. SmO2 is the percentage of hemoglobin and myoglobin that is carrying oxygen in the capillaries and tissues of the muscle. The second is the concept of supply and demand. If demand exceeds supply, SmO2 will go down. If supply exceeds demand, SmO2 will go up. Thank you for taking the time to view this tutorial.